right. Calculus 1 students, I want to do a couple examples about continuity that I like using this definition. I left this definition on the board here. We went over this last time. In order to be continuous at a point C, we have to pass this three-step definition of continuity. And then we can say it's continuous at that point. You don't really say it's continuous everywhere unless you know it is. So you're always investigating a point. Now, I've got a couple examples, but here's one big one first. So I've got an easier one after this I'll come up with. But so this is a hell of a piecewise function. This is a good problem. I always make up these good problems. And so it's a piecewise function. It's split into three pieces. You know, when x is less than 1, it's this. You know, when x is less than 1, it's this polynomial. And we just mentioned in the other video that polynomials are continuous. So when x is less than 1, I got no problems, no discontinuities. When x is between 1 and 3, it's this polynomial, which actually is a line. There's no problems there. Between 1 and 3. And when it's greater than 3, it's a sine function. It looks pretty weird, but I don't think there's any problems greater than 3. So again, so there's no problems except at these places where the pieces might join up or not, which is at x equals 1 and x equals 3. So those are the places I need to investigate. Sometimes there's other issues in here we need to worry about, but not on this example. So in this example, I'm worried about x equals 1. So this is how I do it. I come over here and say, okay, I'm worried about x equals 1. I'm going to go through my three-step definition. Let's try it. Step 1. I need to plug 1 in the function and see if it's defined. So to plug 1 in the function, pay attention to that equal sign there. And when x is equal to 1, we would use this piece of the piecewise function, and I'd plug a 1 in there, and I would get a y value of 5. All right, so the function is defined. Let's try step 2. Step 2 says I want to do the limit as x approaches 1 of this function. Well, of course, that means I'm going to do the limit as x approaches 1 from the left, and I'm going to do the limit as x approaches 1 from the right. That's how I got to do this problem. So I'm writing it out for you. And I encourage you to write things. So, you know, mathematics is a written language. We write back and forth to communicate to each other. You're writing to communicate to yourself. If you just do a little shorthand thing, you know, I don't know. You might get it right, you might get it wrong, but the communication is lacking. Because basically, to do the limit from the left, I am just plugging a 1 in there, and to do the limit from the right, that's when x is bigger than 1, I'm plugging a 1 in there. So this is kind of formal here. I'm encouraging you to embrace this formality here a little bit, but basically you are plugging in a 1 and a 1 to try to see if it matches up. So from the left, you're on the left side of 1, you plug a 1 in there, that's 3 minus 7, that's negative 4 minus 1, that's a negative 5. Okay, from the right, you plug a 1 into here and we get a positive 5. Well, when the left and the right don't match up, what's the answer to this limit? DNE. And we just failed step 2. So we're done. This is a discontinuity. This is a discontinuity. And when it fails this step 2, when the limit doesn't exist, we classify it as a non-removable discontinuity. Non-removable. And that's part of my answer, and that's part of me showing my work. Let's do, what else? Okay, I'm also worried about x equals 3. Let's investigate x equals 3. So I'm moving over here. Sorry. I want to investigate at x equals 3. All right, step 1. What's f of 3? Right, step 1 is f of 3. Plug 3, okay, there it is. Plug 3 in the function. I get, by the way, I'm changing this problem, sorry. I'm going to change this problem. Sorry, don't see the guy behind the curtain, just change that problem. That's okay. I'm plugging in a 3, I get 21 minus 2. I get 19. All right, cool, I get 19. All right, it passes step 1. Step 2. What's the limit as x approaches 3 of this function? Well, again, I'm going to be a little sloppy here. I got to investigate the left and the right, though. Look at, I'm being a little more sloppy with my notation. That's okay. I got to investigate the limit from the left. From the left, I'm on the lower side of 3. I'm on the lesser side of 3, and basically I'd plug a 3 in here and I'd get 19. From the right, I'd be on the right side of 3, and I'm doing this limit. Now, you might say, oh, you're not allowed to plug in a 3. It doesn't equal a 3. Well, I'm not plugging it in. I am plugging it, but I'm doing a limit. I'm doing a limit where I'm allowed to get darn close to 3 from the right. And, this is that theorem from back in 2.2, where 2.3, where we get the sine of 0 over 0. This is a little slightly altered version of that theorem, but if we can get the sine of 0 over 0 and these match up, then that was a 1. So the limit as x approaches 3 from the right, you plug a 3 in here, the sine of 0 over 0 is a 1 from our theorem from earlier in this chapter. That's a 1. Oh, times 19. 1 times 19, that's 19. Well, then guess what? What's the answer to this limit? If the left is 19 and the right's 19, the answer to this limit is 19. All right, step 3. Does the answer to number 1 equal the answer to number 2? Does the function value equal the answer to the limit? And indeed it does. 19 equals 19. So thanks, I made that last minute of adjustment there. And anyway, this function is continuous at 3. We just passed the test. So at 3, I want to write the word continuous. It is not a point of discontinuity. It passed the 3-step definition of continuity. So this is a function. There was no other suspicious points of discontinuity to investigate. The only points to investigate were 1 and 3. 3 passed. It's continuous at 3, and it was discontinuous at 1. It was non-removable. So that's a good problem, man. I like these piecewise problems where you use this definition to investigate. I'm going to erase it and show you another problem. You ready? I'm going to erase this guy. I'm going to show you another problem. This is easier. Maybe I should have started with this. I don't know. It's easier. Watch this. I'm just making this up. So here's a function. And in order to investigate its continuity, in a way I'd use this definition, in a way I don't. Watch, I'll show you what I mean. Really, in a way, I am using this definition. The first thing I'm looking for is where the function might be undefined. To be continuous, it's got to be defined, so I'm looking for where it's undefined to find the discontinuities. My job is to find all the discontinuities. Well, of course, it's undefined when the denominator is 0, so I'm going to factor the denominator. If I factor out an x, I get x and x plus 4. Now, I'm going to go ahead and factor the numerator. The numerator is x minus 4 and x plus 4. It's a nice difference of 2 squares. So I didn't do anything except a lot of factoring there. Factoring's useful. Now, before you cancel anything away, you're tempted to cancel that away. Hold on a second. Is this function undefined? Yeah. And so it fails step 1. The function is undefined, and those are discontinuities. So I have a discontinuity at x equals 0. At x equals 0, the function is undefined. I have another discontinuity at x equals 4, negative 4, right? At x equals negative 4. At negative 4, you get a 0 in the denominator. Those are the 2 bad places. They really are discontinuities. But because this one cancels away, and I don't know if we haven't told you this yet, but maybe I will right now. When you cancel that guy away, he's a whole. He's actually a whole. Now, I wasn't looking for the word whole or asymptote. This other one that doesn't cancel away is a vertical asymptote. And I didn't ask for those words. What I'm looking for is the words, is it non-removable or removable? And the one that cancels away, which is the whole, maybe you recall from the previous video, we call that a removable discontinuity. And I'm just going to add the fact that it's a whole. The one that did not cancel away is called a non-removable discontinuity, and I'll just add the fact that it's a vertical asymptote. It is a vertical asymptote. Asymptote. Cool, end of problem. Those are easy. And did I use the three-step definition? I mean, not really. I mean, I was looking for where it was undefined. I mean, I found two places where it failed step one. These are two places where the function is not defined. It fails step one. I didn't really have to investigate further. These are two places where the function fails step one. I guess if I would have done the limit, I would have found out that because this one's a whole, this limit would have existed, you know? I mean, the limit exists at a whole. So that's why he's removable. This is an asymptote over here. So at an asymptote, the limit doesn't exist. The limit does not exist at an asymptote, so it's non-removable. Or I could just memorize it. The holes are removable because they cancel away. It's like you removed it. Maybe that's the idea. And it's vertical asymptote. It's just non-removable. We're finding discontinuities and we're classifying them with this new language, the type of discontinuity it is, non-removable or removable. You know, the last problem I did, I erased all that work, but that was non-removable because the limit didn't exist. But that wasn't a hole or a vertical asymptote. That was just the left and the right didn't line up. That was what I called a break in the previous videos. The graph was broken. All right, these are good examples. There's plenty more. There's a few other good ideas in continuity. So we're getting toward the end of this chapter, but definitely a few more videos to go. Thanks for working and listening. Do some homework.